Dear student, myself Dr. Surekha Jaiswal, Head Department of Physics, Moreshwar College, Bhokardan, District Jalna. Today we will see course code 101, semester 1st. Now see elasticity. Contents are introduction, Moduli of Elasticity, elastic constant, Young modulus, bulk modulus, Modulus of Rigidity. Now elasticity. Consider a spiral spring fixed at the upper end and pulled downwards. The length of the spring increases. At the same time, an opposing force in the upper direction develops in the spring. When the pulling force is removed, the spring regains its original shape. So, a stretched rubber band regains its original size and when the stretching force are removed, and the force which tends to restore the shape or size of the body are called restoring force. Now in elasticity, the property of a body by virtue of which it resists deformation force and regains its original shape and size when deformation force is removed, so it's called elasticity. And plasticity, a body which cannot regain its original shape and size when the deformation force is removed, is called plasticity. And for example of plastics materials are clay. Now the force applied to a body can produce a change in shape or size or both in shape and size of the body. Such change is called as deformation. By applying suitable force, all bodies can be more or less deformed. So, following points are here. First, change in length. Second, change in volume but no change in shape. And third is change in shape but no change in volume. Therefore, for changing the shape and size of the body, there requires some force. That force is called as deforming force. So that the deforming force is defined as the force which produces deformation in the body. Now elasticity is the property possessed by a material body by virtue of which it regains its original condition when the applied deforming force are removed. Now bodies which can recover completely their original condition on the removal of the deforming force are said to be perfectly elastic. On the other hand, bodies which do not show any tendency to recover their original condition are said to be plastic. Now rubber cord, metal like steel, copper, silver, coal, etc. within the elastic limit are examples of the elastic body. Clay, wax, etc. are the example of plastic body. The internal restoring force per unit area is called as stress. SI unit of stress is Newton per meter square. Now CGS unit of stress is Dyne per cm square. Tensile stress, longitudinal stress, volume stress, shearing stress are the three types of stress. The change in the dimension per unit original dimension is called strain. Strain is a ratio of two similar quantities. It is a pure number, so strain does not have any units. Tensile strain, that is longitudinal strain, volume strain and shearing strain are the three types of strain. Now according to Hooke's law, within the elastic limit, stress is directly proportional to the strain. So we can write modulus of elasticity equal to stress upon strain. So SI unit of modulus of elasticity in Newton per meter square. CGS unit of modulus of elasticity is dyne per cm square. Now, moduli of elasticity, that is elastic constant. The modulus of elasticity is a material property that describes its stiffness and is therefore one of the most important properties of solid materials. Mechanical deformation put energy into a material and the energy is stored elastically or dissipated plastically. The way a material stores this energy is summarized in stress-strain curves. Now, stress is defined as force per unit area and strain is elongation or contraction per unit length. When a material deforms elastically, the amount of deformation likewise depends on the size of the material, but the strain and for a given stress is always the same and the two are related by Hooke's law. Stress is directly proportional to strain. There are three types of modulus of elasticity for solid corresponding to three types of strain and stress. Now, M modulus, that is Y. Within the elastic limit, it is the ratio of longitudinal stress to longitudinal strain. So, Y equal to longitudinal stress upon longitudinal strain. Now, consider a metallic wire of original length L, capital L, and radius R is suspended from rigid support. Let M equal to mass is attached to free end of the wire such that its length is increased by small l as shown in figure C. Now, longitudinal strain equal to change in length upon original length. Now, change in length here, that is a small l. Original length is here, that is shown in figure, that is a capital L. So, L upon L, that is a longitudinal strain. Now, longitudinal stress equal to applied force upon area of cross section. So, applied force is equal to mass into acceleration. So, here mass is capital M and G is here, that is the gravitational force. So, M into G, that is a force upon area of cross section. So, area of cross section as shown in figure, this A equal to pi r square. So, M modulus equal to longitudinal stress upon longitudinal strain. So, M modulus equal to mg upon pi r square upon L upon L. So, after simplification, M modulus equal to mgl upon pi r square into L. Now, bulk modulus, that is K. Within the elastic limit, it is the ratio of bulk stress to bulk strain. So, K equal to bulk stress upon bulk strain, that is, consider here a spherical body of original volume V, seen figure, is subjected to normal force F so that it changes by dV as shown in figure. So, after applying the force F, we get the changes to the original shape of this body. Here volume is changes. So, let A be surface area of the body, then bulk equal to change in volume upon original volume. So, change in volume is here, that is a dV upon capital V. So, bulk stress equal to applied force upon area of cross section, that is equal to F upon A, that is equal to dP, that is change in pressure. So, bulk modulus equal to bulk stress upon bulk strain. So, bulk modulus K equal to F upon A upon dV upon V. So, bulk modulus K equal to V into dP by dV. modulus of rigidity, that is eta. Now within the elastic limit, it is the ratio of shearing stress to shearing strain. So modulus of rigidity equal to shearing stress upon shearing strain. So here consider in figure a rectangular block A, B, C, D as shown in figure with its lower and tangential force, that is applied here, that is a F, is applied to upper layer AB, see in figure. So that the upper layer AB is displaced laterally to A dash to B dash, see in figure, and here having a small angle theta as shown in figure. So shearing strain equal to lateral displacement of layer upon distance of layer from fixed layer. So here lateral displacement of layer is here as shown in figure, having a to A dash and B to B dash. So here lateral displacement is here A to A dash upon distance of layer from fixed layer, that is AD, see in figure, equal to what? That is a tan theta. So if theta is very small, then tan theta becomes theta. So shearing strain equal to theta. Shearing stress equal to applied tangential force upon area of upper surface, that is A. So shearing stress equal to force upon area. Modulus of rigidity equal to shearing stress upon shearing strain. So modulus of rigidity, that is eta, is equal to F upon A into theta. Thank you.